Machine learning and deep learning. About this course. Machines can learn. They might begin performing tasks poorly, but, with the help of artificial intelligence, AI, they can improve their work, becoming experts at something that might take a human many years to learn. In fact, even the AI in your smartphone can use machine learning to reason through subjects that no human has ever been able to master. How is this possible? To find out, you'll explore three categories of AI. The term artificial intelligence describes computer systems that can apply reasoning to subjects that previously required human intelligence. Machine learning can enable systems to predict and classify given data in response to ever-changing data, somewhat like the way you learn from experience. Deep learning is a group of extremely powerful types of machine learning, many of which are inspired by the operation of neural networks in the human brain. This is a diagram depicting the relationship between deep learning, machine learning, and artificial intelligence. Deep learning is circumscribed by machine learning. Machine learning is circumscribed by artificial intelligence. These AI systems do not have common sense or world knowledge, nor do they have a sense of self, at least, not yet. But they do acquire knowledge and understanding through experience, a process called cognition, accomplishing results that resemble human thinking. They do this primarily by using complex rules called algorithms that help them analyze data. Learning objectives. After completing this course, you should be able to distinguish between artificial intelligence, machine learning, and deep learning. Describe supervised, unsupervised, and reinforcement learning. Describe decision trees, linear regression, and logistic regression. List and explain advantages of classical machine learning. Describe how neural networks are inspired by the human brain. Trace the flow of information through a perceptron's nodes. Describe machine learning's trial and error learning process. Define and describe deep learning and its ecosystem. Identify real-world applications for the deep learning ecosystem. Explain generative AI and the impact in today's world. Identify future trends for machine learning. About this module. Module 1. How do machines learn? Introduction. In this module, you'll learn how machine learning and its subset, deep learning, fit into the continuum of artificial intelligence. You'll also explore three different approaches that data scientists take when training AI systems. Learning objectives. After completing this module, you should be able to distinguish between artificial intelligence, machine learning, and deep learning. Describe supervised, unsupervised, and reinforcement learning. Machines learn in three general ways. AI systems use algorithms to predict and classify data points collected both from computer databases and natural occurrences. But algorithms have three general ways that they can learn from this data to get better results and provide better predictions. Supervised learning, unsupervised learning, reinforcement learning, supervised learning. In supervised learning, humans give an AI system what's called structured data. This is a set of facts and figures arranged into neat, labeled categories, the way you might put weather information into a table. For 4 hours of study, the final day value is 80. For 6 hours of study, the final day value is 90. For 8 hours of study, the final day value is 100. Using the way the data has been structured, the AI system can detect patterns, such as day-to-day temperature changes in the table above, and use those patterns to predict future data, such as temperatures during the following week. A single rose flower. Structured data can also take the form of images. If, for example, the data includes photos of flowers, some of which are roses and are labeled rose, the machine will learn things about the arrangements of pixels in those photos. Later, when it sees a new rose photo and is asked, "What is this?" it will respond rose. As you'll soon discover, the machine will never give this result with absolute confidence. Instead, the system will give a confidence value to indicate, for example, that it might predict with 85% certainty that its answer is correct. The more data the system ingests, the higher its accuracy will be. Unsupervised learning. It has often been convenient to refer to plants or their behavior in terms implying reasoning faculties. Of course, plants are never reasoning things, reasonable as many of their actions appear to be, and to ascribe such qualities to them is to saddle them with attributes perfectly foreign to the plant world. Source: Project Gutenberg. Royalty-free text, opens in a new tab. In contrast to supervised learning, unsupervised learning trains a machine with unlabeled data, such as the text of a book. Training an AI system with unlabeled data is more difficult because the system can't make predictions until it has structured the data itself. In the book example, structuring the data would involve breaking down the text and finding relationships between words and sentences. So, algorithms explore the data and try to find structure. For example, a system might be fed many articles about different kinds of plants and form its own conclusions of their attributes. When the system ingests new text describing a plant, it identifies it and gives it a confidence value. Reinforcement learning. With reinforcement learning, a machine is not given specific information to ingest. Instead, it learns through trial and error. The machine's algorithms are rewarded when it performs a correct action and penalized when it doesn't. Photograph of a dog's head. Suppose the system is given a photo that probably depicts a dog, and it's asked, "Is this a dog?" Remember, it has been fed little or no structured information about dogs. The machine answers yes or no, and gives itself a confidence value that is somewhere between 100% correct and 100 reinforcement learning % incorrect. Then it is given new information indicating whether that answer really was right or wrong. This is where the reinforcement takes place. For each answer that's largely wrong, the machine is penalized, its algorithms are adjusted and the picture is sent back for another try. But for each answer that's largely correct, the algorithms are rewarded. After these penalties and rewards happen many times, the machine's answers become more accurate and its confidence value grows higher. This is particularly useful when a machine needs to work on a specific type of problem. The machine continuously makes decisions until it reaches a long-term goal. Each decision the machine makes is based on the previous decision. This is common in an area like game playing, where a series of moves can win or lose a game. What do you think? Try reinforcement learning yourself. Supervised learning requires that an AI system ingests structured data. Unsupervised learning and reinforcement learning require a system to develop its own structure either by analyzing large amounts of data, unsupervised learning, or by trial and error, reinforcement learning. How do machines learn? You might be wondering how machines learn and asking yourself, how do they do it? To find out, this course guides you through two different technologies by which machine learning takes place: classical machine learning and members of a group of technologies called the deep learning ecosystem. Studying these two machine learning technologies is like looking under the hood of two automobiles, one gasoline-driven and the other electric, to learn how each one makes the wheels turn. In this case, the two engines are classical machine learning and the deep learning ecosystem. About this module. Module 2. Classical machine learning. Introduction. In this module you'll learn how classical types of machine learning explore unstructured data, and you'll identify situations where these methods remain useful today. Learning objectives. After completing this module, you should be able to describe decision trees, linear regression, and logistic regression. List and explain advantages of classical machine learning. Describe and explain how a sigmoid function is used in machine learning. Classical machine learning. Classical machine learning began in the 1950s. AI systems learned by ingesting data and getting better at recognizing patterns. The AI systems could predict things like the distance between points or the intensity of values. Like all machine learning, the classical form depends on algorithms. Recall that algorithms are mathematical expressions that output a result. Classical machine learning uses a small number of algorithms in a relatively simple arrangement. Sometimes machine learning algorithms are binary, which means that they output one of only two values. Typical binary results might be a 1 or a 0, a yes or a no, and a true or a false. Other classical learning algorithms are more complicated. For example, their result might be represented as a position on a multidimensional graph rather than this point or that point. Here are three typical algorithms that are used in classical computing. Decision tree. Linear regression. Logistic regression. Decision tree. A decision tree is a supervised learning algorithm. It operates like a flowchart. You can think of a flowchart as an upside-down decision tree. The flowchart has a root node, where the flowchart begins, branches that connect to internal nodes, and more branches that connect to leaf nodes. Explore these features in the following diagram, which depicts a decision tree about whether this is a good time to surf on the ocean. This flowchart outlines a step-by-step decision process to determine if conditions are suitable for surfing. Here is how the decision tree breaks down. The process begins by asking, is there swell? If there is no swell, no, the conclusion is don't surf. If there is a swell, yes, the next factor to evaluate is the wind. If there is low to no wind, the conditions are good, and the decision is to surf. If there is high wind, you must then evaluate the wind direction. If the high wind is onshore, the final decision is don't surf. If the high wind is offshore, the conditions are favorable, and the decision is to surf. What do you think? Try running your own decision tree analysis about swell, which is a type of ocean wave preferred by surfers. How would you answer this question? If there are offshore waves but little wind, is this a good day to bring your surfboard to the beach? How does a classical machine learning system use a decision tree? It starts with a known set of data, like this one. D1, on day 1, the outlook was sunny, the temperature was hot, humidity was high, the wind was weak, and the answer to surfing was no. D2, on day 2, the outlook was sunny, the temperature was hot, humidity was high, the wind was strong, and the answer to surfing was no. D3, on day 3, the outlook was overcast, the temperature was hot, humidity was high, the wind was weak, and the answer to surfing was yes. D4, on day 4, the outlook was rain, the temperature was mild, humidity was high, the wind was weak, and the answer to surfing was yes. D5, on day 5, the outlook was rain, the temperature was cool, humidity was normal, the wind was weak, and the answer to surfing was yes. D6, on day 6, the outlook was rain, the temperature was cool, humidity was normal, the wind was strong, and the answer to surfing was no. D7, on day 7, the outlook was overcast, the temperature was cool, humidity was normal, the wind was weak, and the answer to surfing was yes. D8, on day 8, the outlook was sunny, the temperature was mild, humidity was high, the wind was weak, and the answer to surfing was no. D9, on day 9, the outlook was sunny, the temperature was cold, humidity was normal, the wind was weak, and the answer to surfing was yes. D10, on day 10, the outlook was rain, the temperature was mild, humidity was normal, the wind was strong, and the answer to surfing was yes. D11, on day 11, the outlook was sunny, the temperature was mild, humidity was normal, the wind was strong, and the answer to surfing was yes. D12, on day 12, the outlook was overcast, the temperature was mild, humidity was high, the wind was strong, and the answer to surfing was yes. D13, on day 13, the outlook was overcast, the temperature was hot, humidity was normal, the wind was weak, and the answer to surfing was yes. D14, on day 14, the outlook was rain, the temperature was mild, humidity was high, the wind was strong, and the answer to surfing was no. With some mathematical calculations, a classical AI system can digest this table plus additional information about dates and waves, possibly from a different source. Then, the system can make a reasonably accurate prediction about surfing today or any day. Linear regression. Linear regression is another type of algorithm. It relates to data that might be graphed as a straight line. For example, a business might believe that more advertising spending leads to better sales. This could be graphed as a series of dots that form a rising straight line, as depicted here. Simple chart showing dots, most of which rise on a straight left-to-right diagonal. The x-axis is labeled thousands of autos sold. The y-axis is labeled sport event ads placed. As suggested in the chart, as advertising increases, so do sales. There are many possible outcomes. Different amounts of advertising lead to different amounts of sales, but the change rises on the graph in a straight line. The situation is more complicated if a company's actual sales show different data for different products, at different locations, on different dates, and so on. With a large number of variables and instances, the graph becomes a mass of dots that don't arrange into a straight line at all. Without adjustment, resulting graph is too general to help a business make a good decision. That's where linear regression can help. Linear regression can learn all the variables, then calculate a reasonably accurate prediction of how advertising will impact sales at some time and location in the future. In effect, linear regression resolves the mass of dots into a most likely line that can be used for simple prediction. Logistic regression. In some situations, a relationship does not fall in a straight line. Sometimes a system uses values that require a specific, limited kind of outcome, such as something between 0 and 1, or no and yes. In this situation, a graph can form what's called a sigmoid function, or an S-shaped curve, as shown in the accompanying example. For any set of variables, the outcome, which is a point on the S-curve, falls between 0 and 1. An S-shaped curve showing that as hours of studying increase, the probability of earning a passing grade rises from nearly 0, almost no probability, to nearly 1, almost 100% probability. Here's a real-world example. Refer to the previous graph. Let's say you want to know how many hours you should study in order to pass an exam. You have the number of study hours and passing or failing status for 10 other students. Hours of studying is a varying amount, in this case, between 1 and 5 hours. Passing the exam is a matter of no or yes, either fail or pass. If you plot these two factors together as a logistical regression, you get an S-curve in which 0 hours of study results in a very low chance of passing, while 5.5 hours results in a very high chance. As shown in the chart, the variable hours of studying is along the x-axis. The values along the y-axis represent the values for the variable probability of passing exam. Here's another way to understand the graph. It predicts that studying at least 4 hours gives you a very good chance of passing the course. Comparing linear and logistic regressions. Linear and logistic regressions are useful in the following ways. A linear regression answers a question such as if this increases by x, how much will y increase? A logistic regression answers a question such as if this increases by x, will the value of y be closer to 0 or 1? What do you think? You likely use 3 forms of classical learning analysis: decision trees, logistic regression, and linear regression in your own life. Next, try this sorting activity to review these concepts. An exam passed or failed is binary, yes or no, so relating it to hours studied would use logistic regression. More AP classes passed leading to more college acceptances would use linear regression. Deciding a major would use a decision tree based on professors' names and personal interest. Classical machine learning is not obsolete. Classical machine learning can be outperformed, at some tasks, by newer methods that are part of the deep learning ecosystem. But there are still reasons to use classical machine learning. These include: work with structured data, lower expense to operate, easier to interpret. Select each reason to learn more about using classical machine learning. Work with structured data. Classical machine learning is used mostly with structured data from databases, such as hours studied compared to grades earned. Lower expense to operate. Classical machine learning requires less computing power than deep learning ecosystems. They can run on less expensive computers with less powerful processors, which lowers the price for smaller businesses, communities, or healthcare systems that share time on them in pay-as-you-go arrangements. Easier to interpret. Deep networks are so complex that even AI researchers don't entirely understand what's going on inside. As a result, AI researchers are not always able to determine when deep network systems are producing invalid outputs. Compared to these mysteries, classical results can be easier to debug, and to test for accuracy and lack of bias. For these reasons, classical learning systems are still useful today. About this module. Module 3. The Deep Learning Ecosystem. Introduction. Neural networks are inspired by human brain cells. In this module, you'll learn how neural networks can greatly enhance an AI system's ability to analyze complex data and improve its results through trial and error. Learning objectives. After completing this module, you should be able to describe how neural networks are inspired by the human brain. Trace the flow of information through a perceptron's nodes. Describe machine learning's trial and error learning process. Define and describe deep learning and its ecosystem. Inspired by the human brain. Today, machine learning has evolved into a collection of powerful applications called the deep learning ecosystem. The foundation for many applications is called a neural network. A neural network uses electronic circuitry inspired by the way neurons communicate in the human brain. In the brain, cells called neurons have a cell body at one end where the nucleus resides, and a long axon leading to a set of branching terminals at the other end. Neurons communicate to each other by receiving signals into the axon, altering those signals, then transmitting them out through the terminals to other neurons. Researchers estimate that a human brain has about 100 billion neurons, each one connected to up to 10,000 other neurons. In a neural network, a building block, called a perceptron, acts as the equivalent of a single neuron. A perceptron has an input layer, one or more hidden layers, and an output layer. A signal enters the input layer and the hidden layers run algorithms on the signal. Then, the result is passed to the output layer. Select each number in the following diagrams to compare the structures of a living neuron and a neural network's perceptron. Biological input. A signal passes from the terminal of one neuron into the axon of another, using a combination of electrical and chemical reactions. Biological input and response. Signals enter the cell body, which computes a response that then emerges from the other end of the cell. Neural network input and response. Similar to the way a signal passes through and is altered by a neuron, a signal enters a perceptron's input layer, then passes through and is altered by algorithms within nodes in the hidden layer. Then the response emerges from the hidden layer and is transmitted onward from the neuron's output layer. The hidden layers in a neural network resemble, as a group, the long cell body that connects dendrites to axons within a human brain cell. Those hidden layers contain nodes. Each node runs an algorithm and bits of additional code to test and adjust its result. When the value reaches a certain threshold, the node fires. Note: a node often uses a sigmoid function to determine whether or not to fire. As explained previously, a sigmoid function can generate a binary answer, such as yes or no. The binary answer tells the node whether or not to fire. You can think of the threshold as a hurdle a solution must jump over to give a result of yes. If there are other nodes connected to the node, they are activated when the signal reaches them. If the other nodes reach their own thresholds, then they fire. The signal cascades down through the hidden layers in a way that's somewhat similar to how a signal passes down the body of a human brain cell. Keep in mind that these resemblances are only similarities. Neural networks are inspired by the human brain, but the activities inside neural networks are quite different. A path through a neural network. The operation of a neural network is pure mathematics. The network isn't thinking, it is calculating. But it's using those calculations to create an output that humans can interpret as an answer or a recommendation. For example, consider the following scenario: Mark is trying to decide if he should order a pizza. Mark wonders how a neural network might respond to the question, "Should I order a pizza?" The following scenario provides the step-by-step flow of decision-making as individual nodes perform algorithms and pass on their results. Introduction. Should I order a pizza? Step 1. Should I order a pizza? I'll ask the neural network. This is a perceptron diagram with one hidden layer of 3 nodes. The focus of the diagram is the input layer. This neural network has already been trained. It has learned many things about Mark's past pizza buying behavior, so it's ready to suggest whether Mark is likely to order one today. Today, the neural network is going to invoke 3 things it has observed. Mark usually orders ahead. Mark is trying to lose weight, so lately he's ordered pizza less often. Mark's email includes a coupon for a free pizza. Now Mark asks, am I likely to order a pizza today? Step 2. Ordering ahead. A perceptron diagram with top hidden layer node as the focus of the diagram. One node in the hidden layer looks up Mark's buying pattern and observes that Mark always orders ahead. So, the node assigns ordering ahead a value of 1. For clarity, 1, 1, and 0, 0, values are used. The system has learned something else about Mark's ordering. Mark gives more weight to some factors than others. So, the system gives each factor a weight based on Mark's past behavior. The more Mark tends to do something, the higher the weight. Mark always orders ahead, so the system gives today's order ahead factor a weight of 3. Multiplying the initial value, 1, by the weight, 3, gives the node an output value of 3. So far, the total value of the ordering factor is 1x3 equals 3. Step 3. Getting salad instead. A perceptron diagram with middle hidden layer node as the focus of the diagram. The next node in the hidden layer registers that, lately, Mark has been ordering a salad about half the time. So, the node gives the salad option an initial value 0.5. The system also knows that Mark is not consistent about avoiding pizza for his diet, so it gives the option to order a salad a weight of 0.5. The initial value, 0.5, multiplied by the weight, 0.5, is 0.25. 0.5x 0.5 equals 0.25. Step 4. Free coupon. A perceptron diagram with the bottom hidden layer node as the focus of the diagram. The third node in the hidden layer knows that Mark has a coupon for a free pizza. So, it gives the coupon a factor of 1. Finally, the system observes that Mark always uses free coupons as fast as they arrive. So, the system multiplies the coupon factor by a weight of 5. 1x5 equals 5. With these algorithms now run, the system advances results from all 3 hidden layer nodes to the output node. Step 5. Weighting the answers. A perceptron diagram with the output layer as the focus of the diagram. The hidden layer has one more step to perform, using an activation algorithm. This is an algorithm that will fire only when the total weight from Mark's preferences algorithms reaches a certain threshold. Suppose that, for pizza, the threshold is reached when the total weight is greater than or equal to 6. The final node adds all 3 factor values. The result is 8.25. 3 plus 0.25 plus 5 equals 8.25. That's greater than the threshold of 6, so it's pizza for supper tonight? Pizza with generous toppings. Enjoy. As the previous scenario illustrates, in a neural network, individual nodes in a layer work on algorithms simultaneously. The nodes not only calculate but also adjust themselves in response to external factors. This is machine learning. Machine learning is often trial and error. Previous lessons in this course covered how a neural network makes decisions based on what it learns. But you might still be wondering, how does a neural network learns in the first place? The answer is, by continuously adjusting itself, in a process that humans refer to as trial and error. Once a neural network has ingested or already learned a certain amount of data, it stores the data in its body of information, called its corpus. In order to learn, the neural network constantly tests new data or the results of its calculation against its corpus. If the network determines that the new data or results don't match the patterns it has already established, it modifies those patterns for a better fit. Sometimes, to improve a single match, the network tests hundreds or thousands of modifications very rapidly and makes adjustments. Then, the network tests to determine if the match is improving. So, step by step, the machine learns. To visualize this, imagine that someone blindfolds you. They tell you that your assignment is to climb a hill and reach its exact top using the fewest number steps possible. Then, they send you walking up the hill. What do you think? Do you think your assignment is easy? Machine learning makes many guesses. Machine learning uses its tremendous calculation speed to make many guesses that bring it closer and closer to an answer. It randomly makes its first guess, sets that guess as a variable, then tests how accurately the guess fits with both old and new data. Next, it makes an adjustment to the variable and tries again. Using mathematical processes to help it choose right size adjustments, the system keeps on trying, getting closer and closer to perfection but never quite reaching it. For this reason, many AI systems output a confidence value along with an answer or prediction. For example, a system predicting effective treatments for a cancer patient might output 2 or 3 suggested approaches, along with a measure of how confident it is that each treatment might work. This reflects how the system reaches those decisions. The system also leaves the final decision to the doctor who knows the patient. Any computer can perform at least a crude kind of machine learning based on cycles of estimation. Classical machine learning can do it, too. But depending on the complexity of a problem, a conventional computer or even a classical system might take days, or centuries, to reach a conclusion. In many modern applications of AI, the unstructured data involved is complex enough to overwhelm even a simple perceptron, such as to decide whether to order pizza in a previous lesson. So, a perceptron requires more brain power in the form of deep learning. Deep learning relies on multiple layers of nodes, even multiple groups of perceptrons with multiple layers of nodes, to finish the work in reasonable time. From perceptrons to deep learning. A visual diagram: a deep neural network consisting of an input layer, multiple hidden layers, and an output layer. In a previous lesson, Mark ordered a pizza using a perceptron in which one hidden layer of nodes did most of the work. But advanced AI systems use many hidden layers whose algorithms pass the results of sophisticated calculations. This is a deep neural network, DNN. DNN layers can be arranged in groups or elaborate blocks of groups for greater power. DNNs can even be doubled in competing teams that judge and learn from each other's mistakes, without human intervention. This creates powerful reinforcement learning. Select each photograph and the arrows to learn what DNNs can do. Photo identification. Technologists can use a DNN to examine an historic photo of unknown persons or places. The DNN compares what it finds with millions of pictures in its corpus and then outputs full names and possible locations. Housing construction. Real estate companies use a DNN to predict changes in housing prices across an entire city or state. DNNs can help real estate companies predict business trends and determine how to invest in materials and labor. Self-driving cars. Automobile engineers can use DNNs to model millions of driving situations and help self-driving vehicles navigate safely. Cancer treatment. Radiologists can use DNNs to identify variations in MRI images that are otherwise invisible to the human eye. Radiologists can receive early warnings of potentially treatable cancers. An internet search for deep neural network examples can reveal many additional ways that machine learning impacts your life. Many forms of DNN devices make up the modern deep learning ecosystem. About this module. Module 4. Generative AI. Introduction. Generative artificial intelligence, AI, is a powerful and exciting type of AI that generates new, original content, such as images, music, videos, data, code, responses to questions, and a whole lot more. It's a technology that is revolutionizing the way people live, work, and enjoy their leisure time. In this module, you'll learn the foundational concepts of generative AI. Learning objectives. After completing this module, you should be able to define generative AI. Describe how generative AI works. Identify some examples of generative AI applications. Describe the impact of generative AI to businesses. Identify some current limitations of generative AI. What is generative AI? Generative AI is a type of artificial intelligence that creates new, original content that people have never seen before. Most AI systems are discriminative AI models, which predict and classify data. In contrast, generative AI models are a type of deep learning AI system that uses algorithms to generate content based on a submitted prompt, thus the name of generative AI. For example, a discriminative model could tell a bicycle from a truck, and a generative model could generate a new image that looks like a bicycle. So, generative AI's distinction from other AI systems is its ability to produce content that is new and considered creative, such as images, videos, music, synthetic data, essays, answers to questions, and more. Here's a quick example of how easily generative AI can create new images. A person typed butterflies, flowers, mountains in the text prompt of the image generating tool called Free Image Generator. The tool instantly created the following 4 images. Generative AI's output has gained global attention due to the uniqueness, high quality, and speed of content generation. Generative AI is a revolutionary change that's as radical to global humanity as the invention of electricity and automobiles. Let's see how generative AI works. How does generative AI work? Think of generative AI as a virtual artist. Just like a human artist, it needs inspiration and tools to create something unique. Instead of using paint and canvas, however, generative AI uses algorithms and data sets. Here's the overall generative AI process. 1. First, a person feeds the AI a large amount of data. This could be anything from images and sounds to text and numbers. 2. Then, the AI analyzes this data, looking for patterns and relationships between the different pieces of information. The neural network is trained on a dataset of examples of the type of output it is intended to generate, such as images or text. During the training process, the neural network learns to identify patterns and relationships in the input data and use them to generate new outputs that are similar to, but not identical to, the examples it was trained on. 3. Next, the AI uses what it has learned to create something new. The neural network generates new outputs by inputting a random seed value. The seed value serves as the starting point for the generation process. The neural network processes the seed value and generates a new output that is based on the patterns and relationships it learned during training. For example, if someone gave the AI a set of images of dogs, it might use its knowledge of different dog breeds to create an image of a new dog that doesn't exist in real life. Generative AI can also complete more complex tasks, like writing stories or composing music. In these cases, the AI analyzes patterns in language or music to create something entirely new. Of course, not all generative AI is perfect. Just like human artists, sometimes the results can be a bit strange or unexpected. However, as this technology improves, you can expect to see even more impressive creations from generative AI in the future. Types of generative AI models. Let's explore the 3 primary types of generative AI models. Variational autoencoder, V. Generative adversarial network, GAN. Autoregressive. To understand these concepts, you'll learn about simple analogies for each model. Variational autoencoder, V. Think of variational autoencoder, V, models as a skilled artist who can look at a painting, quickly sketch a simplified version of it, and then recreate a new painting using only that simplified sketch as a reference. The artist is capturing the essential elements of the painting and then using them to create a new work of art. Vs use a similar process. The encoder network compresses the input data into a lower dimensional representation and the decoder network reconstructs the original data from this compressed representation. This allows Vs to capture the underlying structure and patterns in the data, which can then generate new, similar data. Generative adversarial network, GAN. Think of a generative adversarial network, GAN, model as a competition between a skilled forger, the generator, and a talented art critic, the discriminator. The forger creates fake paintings, while the critic tries to determine whether each painting is genuine or a forgery. As the forger improves their technique, the critic becomes more discerning, and this cycle continues until the forger can create near-perfect forgeries. In GANs, the generator creates new data, while the discriminator evaluates the quality of the generated data. The generator tries to create data that is realistic enough to fool the discriminator, while the discriminator learns to better distinguish between real and generated data. This competition leads to the generator creating increasingly realistic content. Autoregressive. Imagine an autoregressive model as a skilled storyteller who listens to the beginning of a story and then continues it by predicting what comes next based on the words and events that have occurred so far. The storyteller uses their knowledge of language, grammar, and storytelling conventions to create a coherent and engaging continuation of the story. Autoregressive models generate new content by predicting the next element in a sequence based on the previous elements. They are particularly well suited for generating text because they can model the conditional probabilities of words and characters in a sentence. Check what you just learned about the models of generative AI. By understanding the three types of generative AI, you can gain a deeper appreciation for the incredible possibilities that technology offers for creative expression. Whether you're a musician, artist, or writer, generative AI can be a powerful tool to help you explore new ideas and push the boundaries of your craft. As the field of generative AI continues to evolve, it's exciting to imagine what kind of new and innovative creations we'll be able to generate in the years to come. Examples of generative AI applications. Generative AI is revolutionizing the way people live, work and play. Let's review the following examples of generative AI systems and applications. Chat. OpenAI launched ChatGPT, an AI chatbot, in November 2022. Able to interact by using conversational natural language, this AI tool goes beyond the traditional search engine responses of simply listing related results. Instead, ChatGPT follows instructions given in the prompt and provides a detailed response. For example, with ChatGPT, a person can enter a text prompt of "write a poem about cats" and the result will be a poem about cats, rather than a listing of websites about cats. IBM Watson Discovery uses foundational technologies, such as large language models, LLMs, to obtain insights from what it is that we don't know that we don't know. It's used widely in genomic research, discovering what amino acids might lurk inside the protein not known before and unearth the relationship of various actors or entities for government security-related questions. DALL-E and DALL-E 2. Developed by OpenAI, these are generative AI models that use natural language text input to generate digital images. The first version of DALL-E could only render AI-created images in a cartoonish fashion, but the latest version can produce much more realistic images due to improved image processing algorithms. Bard is a generative AI tool that Google launched in an initial, limited capacity in March 2023. Bard is founded on Google's bidirectional encoder representations from Transformers, BERT, model. It isn't generative AI, rather, Google developed it for natural language processing, NLP, especially for its capacity to interpret the nuances of a user's search words. Bard builds on BERT's capability of natural language interactions with Bard's generative AI capability to generate new content. For example, musicians can use Bard to compose music and lyrics. Generative AI is a rapidly developing technology and is an extremely dynamic area that is experiencing continuous innovations and advancements. Industry uses of generative AI. Generative AI is already impacting, and will increasingly impact, a wide range of industries, including sports, entertainment, healthcare, retail, banking, manufacturing, engineering, security, media, agriculture, and the list goes on and is continuing to expand. Review these real-world examples of generative AI in practice. Sports. In sports, generative AI can help improve athletic performance and enhance fan engagement. One application of generative AI in sports is the creation of personalized workout plans. By analyzing an athlete's biometric data, generative AI can create customized workout plans tailored to the athlete's fitness level and goals. This technology can improve athletic performance by providing athletes with targeted and efficient training regimes. Another application of generative AI in sports, around fan engagement, is the creation of realistic 3D models of athletes for use in sports video games and virtual reality experiences. By using generative AI, game developers can create highly realistic and personalized virtual athletes that can interact with users in real time. This technology can enhance fan engagement by providing users with immersive and engaging sports experiences. Generative AI can analyze sports data and identify patterns and trends that can inform coaching strategies and player selection. Overall, generative AI has the potential to transform the way people play, coach, and experience sports, enabling new levels of personalization, efficiency, and engagement. Use case. The Miami Dolphins, an American football team in the United States, are using generative AI to improve player performance and prevent injury. They are collaborating with a company called Blue River Technology to develop a computer vision system that uses generative AI to analyze video footage of players and identify areas for improvement. The system analyzes players' body movements and identifies areas where they could be at risk for injury. By using generative AI in this way, the Miami Dolphins can identify potential issues before they become serious problems, enabling them to take proactive measures to prevent injuries and improve player performance. This technology has the potential to transform the way that sports teams approach player health and performance, improving the overall quality of play and reducing the risk of injury for athletes. Entertainment. In the entertainment industry, generative AI can help create new and immersive experiences for users. One application of generative AI in entertainment is the creation of a wide variety of highly realistic and personalized virtual characters and environments for video games and virtual reality experiences. For example, generative AI can create realistic facial expressions and body movements for virtual characters, enhancing the user experience and immersion. Another application of generative AI in entertainment is the generation of personalized music playlists. By analyzing a user's listening history and preferences, generative AI can create unique and personalized music playlists that cater to each individual user's tastes. This technology can enhance the user experience by creating highly personalized and engaging music experiences. Use case. Amper Music uses generative AI to create original music for video games, films, and other multimedia projects. Their platform allows users to input parameters such as mood, genre, and tempo, and then generates a unique and original piece of music in real time. It generates music using a generative model that is trained on a large dataset of musical patterns and structures. By using generative AI to create music, Amper Music can offer highly customizable and original compositions tailored to each individual project's needs. This technology has the potential to transform the creation of music for multimedia projects, enabling more efficient and personalized music production. Healthcare. In healthcare, generative AI can help improve disease diagnosis, medical imaging, and personalized medicine. One application of generative AI is in the generation of synthetic medical images, which can train machine learning algorithms and improve disease diagnosis. For example, generative AI can generate synthetic medical images of rare diseases, which can be difficult to obtain in real life. Another application of generative AI in healthcare is the creation of medical simulations. These simulations can help train healthcare professionals and reduce medical errors. By generating synthetic patient data, generative AI can also train predictive models and improve personalized medicine. Generative AI has the potential to transform healthcare by enabling the creation of realistic medical simulations, improving disease diagnosis, and enhancing personalized medicine. Use case: Path AI uses generative AI to improve the accuracy of disease diagnosis through the analysis of medical images. Specifically, Path AI has developed a deep learning algorithm that can accurately detect cancer cells in digital pathology images. This algorithm was trained on a large dataset of annotated pathology images using a variational autoencoder, V, generative model. The V learned the underlying structure of the pathology images to generate synthetic images that were like the real images in the training set. By training their algorithm on both real and synthetic images, Path AI was able to improve the accuracy of their cancer detection algorithm. This technology has the potential to improve the accuracy and speed of cancer diagnosis, to ultimately improve patient outcomes. Business. In business, generative AI can help improve decision-making, personalize customer experiences, and enhance operational efficiency. One application of generative AI in business is the generation of synthetic data. By generating synthetic data, companies can augment their existing datasets and improve the accuracy of predictive models. For example, a financial institution could generate synthetic financial data to train their predictive models and improve risk management. Another application of generative AI in business is the creation of personalized product recommendations. By analyzing a customer's purchase history and preferences, generative AI can create personalized product recommendations tailored to each individual customer. This technology can improve customer satisfaction and increase sales. People are also using generative AI to improve operational efficiency by creating synthetic data for testing and validation. Generative AI has the potential to transform the way businesses operate by improving decision-making, enhancing customer experiences, and increasing efficiency. Use case: Sentient uses generative AI to develop low-power, high-performance deep learning chips for a range of industries, including smart home devices, wearables, and voice-controlled devices. Their deep learning chips are designed to process data on the device itself, rather than relying on cloud-based processing, which can reduce latency and improve privacy. To train their deep learning models, Sentient uses a generative adversarial network, GAN, to create synthetic data by generating new data samples that are similar to the training data. By training their models on both real and synthetic data, Sentient was able to improve the accuracy of their deep learning chips, making them more reliable and efficient. This technology has the potential to transform the way that companies design and manufacture deep learning chips, enabling a new generation of low-power, high-performance devices. Generative AI is impacting today's world, across many industries. How scientists and businesses are applying AI to different use cases will continue to grow. Limitations of generative AI. As you continue to dive deeper into the world of generative AI, it's crucial to consider the limitations and ethical concerns surrounding these groundbreaking technologies. With models like GPT-4 transforming the way content is created, from text and images to music, it's essential to strike a balance between their extraordinary potential and the need for responsible, equitable usage. Explore these key challenges and ethical dilemmas that come with harnessing the power of generative AI. Limitations of generative AI. Lack of originality. Generative AI models rely on large datasets to learn and generate content. As a result, they might not create entirely original content but rather mimic patterns from their training data, which can lead to a lack of creativity and innovation. Incompleteness. While generative AI models are becoming increasingly sophisticated, they still struggle to understand the nuanced contexts and might generate incomplete or nonsensical content. Bias: generative AI models can perpetuate existing biases present in their training data, leading to the generation of biased content that might reinforce stereotypes and discriminatory behavior. Computational resources: training and deploying generative AI models require significant computational power, which can be expensive and contribute to environmental concerns such as energy consumption and carbon emissions. Ethical concerns of generative AI. Misinformation and fake content: generative AI can create convincing fake content, like deepfakes or falsified news articles, which can lead to the spread of misinformation and have severe consequences for individuals and societies. Intellectual property and copyright: generative AI can produce content that resembles copyrighted material. This raises questions about intellectual property rights and potential infringements. Privacy: generative AI can create realistic images and text about individuals, potentially violating their privacy and causing harm to their reputation. Loss of human touch: as generative AI becomes more prevalent, there is a risk that the human touch will be lost in various creative domains, potentially leading to a decline in the appreciation of human-created art and culture. Unemployment and job displacement: the rise of generative AI might lead to job displacement in creative industries, as machines take over tasks previously performed by humans. Overall, while generative AI has many potential applications and benefits, it's important to be aware of its limitations and potential pitfalls to use it effectively and ethically. Reflection: what do you think? Should students in school be permitted to use generative AI tools to complete their class assignments? Why or why not? Evaluate your thinking. Does your answer account for the following? Generative AI is a tool that is readily available to everyone. So, consider this as a change in thinking that is occurring. As students use generative AI, they will need to consider the limitations. For example, students will need to review the generated content to assess if there are any biases, errors, omissions, misinformation, or a lack of originality. And then the student will need to take corrective actions to address those issues. In addition, instructors know that generative AI is easily available and powerful, so class assignments might change from asking students to write an essay to asking them to assess the essay that generative AI created and report on the embedded limitations, their related implications, and provide solutions to them. About this module. Module 5. Future AI Trends. Introduction. In this module, you'll learn what research scientists believe can be the future of machine learning and its ability to enhance human life. Learning objectives. After completing this module, you should be able to identify future trends for machine learning. Where does AI go from here? A diagram depicting 3 levels of AI: narrow intelligence, developed between 2010 and 2015, broad intelligence or AI for the enterprise, which is available today, and general AI, which is predicted to be available around 2050 or beyond. General AI is the focus of the diagram. You live in the second level of AI, called broad AI, in which machine learning systems have begun to appear in your everyday life. Broad AI can't think abstractly, strategize, or use previous experience to come up with new, creative ideas. But data scientists and programmers are already working on the third level, called general AI. The goal of general AI is to create systems that can perform any intellectual task that a human being can and more. Some scientists believe that this goal may be reached in about 20 years, the early 2040s. What's in store for the future? Scientists at IBM Research predict world-changing advances in AI technology and its relationship with humans. The IBM Research scientists predict that these advances will result in machine-based common sense that can help humans make better judgments. Select each tab to explore what you might experience with AI during your lifetime. AI everywhere. Soon, AI will support seamless connections across industries, ranging from finance, to education, to healthcare. AI will help people work more productively and create new career opportunities. Industries: healthcare, finance, agriculture, government, education, energy, science, business solutions, deeper insights. New technologies will be able to sense and analyze things at a level of understanding that was never before possible. This includes future-forward technologies with unfamiliar names, like quantum computing. Quantum computing is a dramatically different way to calculate, based on the behavior of subatomic particles. Technologies: quantum computing, distributed deep learning, neuromorphic systems, homomorphic encryption, machine foresight, cognitive discovery, engagement reimaged. New forms of human-machine communication, based on blockchain, conversational bots, and more ideas, will transform how you interact not only with your friends, family members, and co-workers, but also with machines that listen and engage in complex conversations. Interactions: human-machine collaboration, new AI modalities, augmented reality, global trade logistics, blockchain for payments, personalization at scale. Machines will interact with you in ways tailored to your particular desires, habits, and level of comfort. Today, websites already offer merchandise based on orders you've made in the past. Soon, you'll use sites that recognize you and know and understand the things you love. This includes the fashions you follow. Future sites will discuss your fashion preferences with you and offer them perfectly fitted to your size and needs. Ways to personalize: personalized healthcare, microsegmentation, personalized finance, targeted marketing, personalized learning, individualized solutions. What about your future? Take a moment to consider your personal strengths and weaknesses as a human being. Is there something you wish you could do with general AI, some kind of reasoning or understanding, beyond what you encounter today? Is there something that would bring you joy, love, or prosperity? Reflection: what do you think? What is your personal dream for AI? Now consider how technology might make your dream possible. Would you like to be part of a team that develops future AI systems? You've come so far and learned so much. You learned ways that machines can learn, with and without human help, using systems modeled after human brain cells. Now that you've completed this course, you should be able to distinguish between artificial intelligence, machine learning, and deep learning. Describe supervised, unsupervised, and reinforcement learning. Describe decision trees, linear regression, and logistic regression. List and explain advantages of classical machine learning. Describe how neural networks are inspired by the human brain. Trace the flow of information through a perceptron's nodes. Describe machine learning's trial and error learning process. Define and describe deep learning and its ecosystem. Identify real-world applications for the deep learning ecosystem. Explain generative AI and the impact in today's world. Identify future trends for machine learning. Key points to remember: 1. Using advanced mathematics, machines can learn either in classical ways or with neural networks. 2. Machines can learn from structured or unstructured data and teach themselves through trial and error. 3. Machine learning tools include logic methods, such as decision trees, linear regression, and logistic regression. 4. Neural networks, inspired by the human brain, build perceptrons with layers of algorithm nodes to perform complex calculations. 5. Multiple groups of multilayer perceptrons, arranged in different ways, extend machine learning in the deep learning ecosystem. 6. Today, people carry on simple conversations with machine learning AI systems using what is known as broad AI. 7. Generative AI has gained attention worldwide as a revolutionary change for creating new and unique content. 8. In the future, General AI systems will perform unprecedented levels of analysis to help humans improve life on a global scale. Explore more. To explore topics from this course in greater depth, check out these resources. Linear regression opens in a new tab, an IBM site that explains more about linear regression and how it helps AI systems make predictions. Logistic regression opens in a new tab, an IBM site that explains logistic regression and its ability to predict probabilities. Neural networks opens in a new tab, an IBM site that explains how neural networks allow computer programs using methods that reflect the behavior of the human brain.